Thank you, Walter, and everyone for being here. Let me begin by thanking the organizers for giving me the opportunity to give this talk on our recent work. So my collaborators Victor, Martin Mayor, and Itai Han on implementation errors in analog Ising optimizers, and you'll be able to find all the details at this archive reference. So let me begin by explaining what I mean by an analog Ising machine or an analog Ising optimizer. So what I have in mind here is a special purpose device built to solve for the ground state of Ising Hamiltonians, right? So this is my Ising Hamiltonian. But crucially, what I have in mind is that the Ising parameters, the local fields and the couplings, are controlled on the device by some continuous field, such that they'll always be subject to some misspecification, okay? And because we're at AQC, the example you should keep in the back of your mind is always a quantum annealer, right? And such as, for example, the quantum annealers built by D-Wave systems. So you might ask yourselves, why should I want to build such a device? And there's at least growing evidence that maybe such devices could be very, very fast, right? And the example that I like to think of is, for example, the work that was done by the Google and NASA groups, where they showed that incoherent tunneling on a physical quantum annealer could give you a wall clock time advantage over, if you like, simulating that tunneling using quantum Monte Carlo. But there was also this nice work by Andreas and Ames at D-Wave that showed that not only could you get a wall clock time advantage, but you could also get a scaling advantage if you tried to solve the right problem, right? So these kind of real-world advantages, have, I think, motivated a lot of people to try to build these kind of special-purpose devices. But of course, you could ask, what's the price I have to pay, right? And to at least start thinking about this question, I want you to think about how you would try to use one of these devices. So for example, let's say I wanted to solve for the ground state of some Hamiltonian H0, which is my intended Hamiltonian. And I program it onto my analog Ising machine, which in this case is literally a black box. But let's say that you could peek into the box. What you would see is that it actually implemented not H0, but some Hamiltonian, which I'll designate by H sigma, right? And H sigma is some distortion of your intended Hamiltonian. And here the distortion is delta H sigma. Now let's say that besides this error, your device is ideal, and it actually then spits out to you the ground state of H sigma. Now the problem is that depending on what H sigma, the noise is doing, the ground state of H sigma may not correspond to the ground state of H0. So even though your device solved the problem correctly, it ended up solving the wrong problem, so it actually gave you the wrong answer, right? So if, in the context of quantum annealing, my evolution was adiabatic, I would still get the wrong answer. Now, I want to emphasize, we are not the first people who have brought up this problem, right? There's, in the spin glass community, it usually goes under the name of J-chaos or bond chaos. For those of us who've been involved in benchmarking using the D-Wave quantum annealers, we know that its performance can be very sensitive to implementation errors. But even this is not even restricted to our field. There's also this very nice work in the quantum simulation community, which shows that implementation errors can cause very strong deviations in the measurement of your observables. So what are we going to do in this, or at least what am I going to try to cover in this talk? I'm going to try to answer these three questions. The first one is, so if I fix the noise level, how does the probability that the ground state of my intended Hamiltonian H0 remaining the ground state of the implemented Ising Hamiltonian H sigma scale with the problem size, which I'll denote by n? And once I have the answer to this, can I then add or address how must the noise level scale such that I can maintain a fixed probability that the ground state of my intended Hamiltonian remains the ground state of the implemented Hamiltonian? And finally, can the classical repetition codes help us achieve whatever this necessary scaling is? So since I want to focus on the effect of implementation errors on the performance of our device, I'm going to assume that the device is ideal in every other way, so except for the analog errors. So what do I mean by that? I mean that whatever the implemented Hamiltonian is, the device will always return its ground state. Okay? So for example, you can imagine that I have a quantum annealer. It's perfectly coherent. It's a closed system, and I always operate it adiabatically. So I'm going to pick a model for these analog errors. So I'm going to imagine that my H sigma essentially introduces these random variables delta H on my local fields and delta J on my Ising couplings. And I'm going to pick them to be essentially Gaussian random numbers with mean 0 and standard deviation sigma. So sigma is going to be the measure of my noise strength. And for now, let's just pick a single ground state of H0 and a single excited state of H0, which I will then denote by SG and SE respectively. And let me ask, what is the energy difference of these two states under H sigma? Okay? And what I want to ask is, when is this energy difference negative, right? So when does the excited state of H0 become more optimal than the ground state of H0? So now we can make two observations. We first notice that these random variables are completely independent or statistically independent from the ground state that I picked, and they're mutually independent, so I can actually rewrite this energy difference as this, where delta E0 is the energy difference under H0, so this will always be positive. D is the Hamming distance between the ground state and the excited states, and W I'll sometimes refer to as the mass, and essentially this just counts the number of different spin pair orientations between the ground state and the excited states, meaning for every bond, when I calculate this quantity, if it's -1, it contributes +1 to W. So now I can actually answer the question of when is this quantity negative. All I have to do is do this Gaussian integral from -infinity to -z, where z is given by this ratio. And I'm going to denote this probability by P of z. We can look at this probability in sort of the extreme limits. So for example, when z is very, very large, this probability is exponentially small, meaning that when z is very large, the probability for this thing being negative is tiny. But of course, when z, we can take the other limit. When z is very small, then this probability is close to 1/2. But it turns out that actually P of z already becomes sizable when z is of order 1. Okay? So what does this mean? It means that if you consider, for example, low-lying excited states, so excited states that have a delta E that's order 1, and what we call they're topologically non-trivial, meaning they're separated from the ground state by a Hamming distance and a mass that's order n, and so there's a large energy barrier that's between them, then you find that actually P of z becomes sizable already when the noise is going as 1/√n. But this is not exactly what we were after, right? Here, so far, what I've talked about is a single ground state and a single excited state. But what we're really after is for a single excited state to become more optimal than all the ground states. Okay? So to make progress in answering these questions, we have to make a few additional assumptions. So the first one is that we have to assume that the mass and the Hamming distance don't fluctuate significantly between these topologically non-trivial excited states. The random variable eta associated with each excited state we assume to be independent. And we assume that we have, let's say, an effective number n sub es of statistically independent excited states. So with these assumptions, you can now actually answer the question of at least what's the probability that a single ground state remains more optimal than all excited states? And so this is just given by this expression. Now, because 1 minus P of z is less than 1, and we expect the number of excited states to at least scale polynomially in the system size, this already tells you that the probability that a single ground state to remain more optimal than all excited states at a fixed noise level decays exponentially with system size. But of course, your problem may have many ground states. So what's the probability that at least one ground state remains more optimal than all the excited states? So that's now given by this expression, where NGS is the effective number of ground states that you have. Now, since it's unlikely that the scaling of NGS with problem size will overcome the decay of the probability for one ground state to remain more optimal, this expression then tells you that it also becomes exponentially unlikely with system size that one ground state, or at least one ground state, remains more optimal than all excited states. So now, OK, this looks bad. So how must we scale the noise in order to maintain a fixed probability that at least one ground state remains the ground state of the implemented Hamiltonian? So let's take the number of excited states to go as e to the b n to the k, where k equals 0 will correspond to the number of excited states being a polynomial in n. Then a quick calculation will show that the way you would have to scale your noise would go something like this. So 1 over the mass plus the Hamming distance square rooted, or with the n to the k all under the square root. So under the worst case scenario, you would have w and d scaling with n and k being 1. So this would tell you that in the worst case, you would need to scale your noise as 1 over n as your system size grows. OK, so far, this has all been sort of analytical with assumptions, which you may wonder, OK, how valid are these assumptions? So what we did next is we tried to corroborate our results with some numerical simulations. So the first example I'm going to consider is instances defined on a chimera graph with range 3 and with only 2 ground states. Now, for those who are not familiar with the chimera graph, right, so this is the physical connectivity of the current generation D-wave quantum annealing processors. One way to think of it, or what it actually is simply a square grid of unit cells. Each unit cell has 8 spins. And the connectivity within the unit cell is a K44 connectivity. And the maximum degree of a qubit is 6. So what this does is that it forms a non-planar 2D graph. Now, range 3 just means that the couplings in my Ising Hamiltonian go from -1 to 1 in steps of 1/3. And these instances are designed in a very specific way such that they only have 2 ground states, and we know what those 2 ground states are. Now, why is this useful? It's useful because it means that we don't need to have a guarantee that we found the ground state of the implemented problem. All we need to do is find an excited state of the original Hamiltonian that is lower in energy than the 2 ground states according to H sigma. This will guarantee us that H sigma's ground state is different than the original 2 ground states. So what this does is that it actually gives us an upper bound on what PS is. So now what we do is we construct 100 of these instances, and for every instance, we generate 1,000 noise realizations on them. So what does the data look like? So what I've plotted here is the upper bound on the median PS as a function of sigma to the 7/4 n, and I'll tell you what this is shortly. So notice that this is on a log linear scale. So the first thing that I hope you all see is that there's a clear exponential dependence on problem size. Right? So here, the data here includes instances going from n equals 512 to n equals 1,548 with a lot of different sigma values. And the point is that all the data seems to collapse very nicely as a function of the sigma to the 7/4 n. So what this means is that for this particular class of instances, it looks like if I wanted to maintain the performance of my analog Ising machine to solve them, I would need to have the noise scaling as 1 over n to the 4/7, which is close to 1 over square root of n. So you'll see that looking at this, it doesn't look like it's as bad as the worst case. Right? So maybe our estimates here were, really pessimistic. But let me consider another class of instances. So this is not exactly an Ising Hamiltonian. So it belongs to what we call 3 regular 3 XOR set instances. So they involve 3 body Z terms. Notice that at least for the implemented Hamiltonian, all the couplings for these 3 body terms are antiferromagnetic. And the way you pick the IJK is such that every spin interacts exactly with 3 other randomly chosen spins. Now, this class of instances has been studied before in the literature, and it's interesting because it's easy to solve classically using Gaussian elimination, but it's incredibly hard to solve using annealing algorithms. But why is it nice for us? It's nice because we know a priori exactly what the ground state of H0 is. It's a unique ground state, and it corresponds to all spins pointing down. And so just like in the chimera example, I don't need a guarantee of finding the ground state of the noisy implemented Hamiltonian. I just need to find an excited state that has a lower energy than this one ground state, and that allows me to put an upper bound on PS. So these are the results for this instance. So now again, it's a log scale on the y-axis, linear scale on the x-axis. The scaling is now sigma to the 4/3 n. Again, the data shows this clear exponential dependence on problem size. And now the data collapses nicely as a function of the sigma to the 4/3 n, which then suggests that the noise, if you wanted to maintain the performance of your analog device for this class of instances, you would need to scale the noise as 1 over n to the 3/4. And this is actually closer now to the worst case estimate. Right? So it's clear that, or I hope at least I've convinced you, that this exponent is going to be, or is going to depend strongly on the class of instances you're studying, but you can get closer possibly to the worst case estimate. But you might say, well, isn't this why we use repetition codes, right? Repetition codes are supposed to solve or to mitigate this problem, let's say. And there was this very nice work by Kevin, Robin, and Daniel in 2013, where they showed that if you use a classical repetition code that essentially rescales the norm of your Hamiltonian by k, this effectively reduces the noise by square root of k. So essentially, the noise sigma gets rescaled to sigma over square root of k. But for all the examples I've shown you today, this would mean that k must scale as n to the alpha with alpha greater than 1. Okay? And if you imagine you had a scalable architecture where the connectivity degree of a physical spin is independent of the system size, what this would mean is that the number of physical spins per logical spin would grow as a power of n. And this, I think, is not an acceptable cost, right? And again, it highlights the importance of having fault tolerance and the fact that this doesn't cut it, at least for these kind of errors. So, in conclusion, right, I hope I've convinced you that the performance of analog optimizers decays exponentially with system size for a fixed noise level. we've at least corroborated, I guess, our results with at least 2 classes of instances. And I hope I've convinced you that at least repetition codes, at least that we know of currently, are not sufficient for solving this problem. Now, I don't want to be the Debbie Downer at this conference, so let me remind you of important things, right? Things that you already knew, okay? So these arguments that I've presented today, in some sense, are asymptotic in nature, right? We're looking at the large n limit, right? In life, usually we have problems of a certain size and of a certain class that we're interested in, and I have faith in my experimental colleagues that if I give them a size and a class of problems, they probably can always engineer a system that has sufficiently low noise to solve those problems well. As long as you don't ask that device to scale forever, you're OK. Okay? And second, you all knew ahead of time that quantum annealing, or any quantum information processing device, without fault-tolerant quantum error correction, is not scalable, right? So the results I've shown today are, in some sense, just another realization of this fact. So with that, let me thank my collaborators again, Victor and Itai, who it's always a pleasure to work with. And further details can be found at this archive reference. Let me acknowledge our funders, IARPA, and because this work was all done under the QEO program. Thank you.
All right. I think we have plenty of time for questions. So.
Yay, Tameem. Yeah, too late there at the end with the Debbie Downer comment. I'm depressed.
You're already depressed? No, you shouldn't be. OK, but yes.
Yeah, I think the only other point I would mention, I think that would be worth including in your last slide is that this also isn't a critical failure mode either, right? It's not like it's ground state or bust in many applications. And in fact, when we look at heterogeneous and hybrid algorithms, the computational role that these systems are going to play until they can start to incorporate a lot of fault tolerant or error correcting mechanisms will be as like hot starters and approximate heuristics and things like that.
OK, so on the one hand, you're right that if you don't care about the ground, or if your life doesn't end when you don't find the ground state, you might think you're OK. And so this I concede. So one thing that I think is important is to think about the that quantum simulation result that I quoted sort of earlier in my talk. So if, for example, what you want to use your quantum annealer like in this sort of beyond optimization and think about using it as sampling, for example, from a quantum thermal state, that work actually showed that the expectation values between the the intended quantum Hamiltonian and the implemented quantum Hamiltonian, those expectations start to deviate more and more as you get closer to the interesting regime, so near, let's say, the critical point. So if you wanted to start using a quantum annealer, let's say, as a quantum simulator, and you wanted to probe the interesting regime near the phase transition where we don't have, let's say, good classical algorithms to simulate, these analog errors make your life worse and worse because you get more and more wrong answers. So I highly recommend that paper, by the way. I think it's a very interesting read.
Another D-Wave question. I thought that the exponent of 1 sounds very pessimistic to me, and it is. So I'm not quite clear on whether you're saying that this is the worst case scenario that you might expect from this analysis, or that you might expect this from some plausible class of problems, because you seem to make some assumptions about the ground state versus excited state degeneracy that I'm not quite convinced about.
OK. So let's see. Let me go back. So definitely, I'm making, when I say that I think it's unlikely that the number of grounds, this n ground states will overcome this exponential decay here, I'm essentially saying that the growth of the number of ground states with n will be slower than the growth or the decay of this, which in the previous slide depended on the number of excited states. Okay? So that's, if you like, the assumption on the number of ground states. And at least in the paper, we give a plausibility argument why that is. Now, it's true. So here, I'm making an assumption about the form of the number of excited states. Right? Clearly, the worst case is when k is 1, and so it's growing exponentially in n. So I agree that, I mean, this, if you like, right? I mean, this is the worst case estimate based on, our derivation. And, you can take that, so if you think that if there are loopholes in the derivation, you can doubt this result, and that's fine. But I think, again, the examples, I think, are illustrative, right? So for at least this chimera instance, it goes as 1 over, essentially 1 over, or very close to 1 over square root of n. And there's actually results in the spin glass literature that show that for 2D square lattices, it actually goes as 1 over square root of n. But then, of course, this other instance, right, which is interesting, it's much more complicated in some sense than the chimera example, but it shows this other worse scaling, right? So
do you have any reason to believe that there's anything in between, or is this?
Well, I mean, this shows that there's something in between. So for example, if you like, so maybe the way I should have said it is that, let's say this was 1 over square root of n, then this would say that k in my expression was actually 0. So because it would mean it would grow polynomially. The number of excited states would grow polynomially with n. Whereas this one would say that k is less than 1, but greater than 0. So it's saying the number of excited states is actually growing like a stretched exponential. Yeah. So there's a question over there.
Where?
All the way back there.
I might have missed it, but how does this differ from resilience that was introduced in 2016?
Oh, so now that was not my work, so I hope I am not misrepresenting it. So if I remember that work correctly, essentially instances were mined such that essentially errors, or the instances were resilient to this kind of errors, right? Such that the ground state doesn't change. So I think it's similar. But as far as I know, that analysis didn't show these scaling results, as far as I know. It didn't show these kinds of predictions. I mean, it just found those instances by mining, which is important, but yeah.
We have time for one more question while our speaker gets ready.
Right here.
Hi. Very nice talk. Have you looked at what this might do if you're, instead of doing traditional annealing, doing something like reverse annealing, where you're only searching within a certain Hamming distance of a starting state?
Oh. So I don't think this will change that result. The reason is because, let's say you implemented the Hamiltonian, you implemented the Hamiltonian, and you start from some initial state, and whatever the band is will be according to that implemented Hamiltonian. So I guess the question would then be, how do analog errors actually change the other states that you're trying to transfer population to? And I don't know the answer to that. That's an interesting question.